Welcome viewers to the sixth lecture of lecture series on integral differential equation under NPTEL course. Now, in today's discussion we are going to discuss about Adomian decomposition method to solve the integral equation, that is a special type of integral equation that we are considering in last few lectures, that is Volterra integral equation of second kind. Of course, this Volterra integral equation of second kind is of non-homogeneous type. Now, you can recall in last two lectures we have discussed about different methods for solving Volterra integral equation of second kind, which are non-homogeneous equation, using the methods. First of all, we have used the method that is known as successive approximation method. Then we have considered the Laplace transform method. And lastly, we have considered the series solution method. Among these three methods, the second method, that is Laplace transform method, deals with the problem where kernel of the integral equation satisfies a specific form. That means, when the kernel of the integral equation can be written into the form k x minus s, that is the function of k x comma s, two variable functions, can be expressed as a single variable function, say t, where t is actually x minus s. That means, the entire kernel can be written as a variable x minus s, taking x and s together under this factor, that is x minus s. So, this becomes a single variable function if x minus s is replaced by t. If kernel satisfies this condition, then Laplace transform method is applicable. Just for a quick recapitulation, in case of successive approximation method, what we have done, this successive approximation method, we have started with that y0 is equal to f x, where the given equation is y x equal to f x plus lambda integral a to x k of x comma s y s ds, where f x is continuous. In this case, a less than equal to x comma s less than equal to b. This f x is continuous over the interval a comma b, and k x comma s is also continuous over the square of length sides of length b minus a. That means, over a region a comma b cross a comma b, and partial derivative of k x comma s with respect to x is continuous over the same domain. Then first of all, we started with y0 equal to f x, and you can recall that I have given some example and also mentioned, instead of considering y0 x equal to f x, you may consider this equal to 0, that means initial 0th approximation as y0 x equal to 0, or you may consider y0 x equal to 1 or y0 x equal to x, but in general we can follow for the time being that y0 x equal to f x as the 0th approximation. Then you can calculate y1 x by substituting y0 x onto the right hand side of this integral equation. So, that means, this is equal to f x plus lambda times integral a to x k of x comma s y0 s ds, and as a general step we can write y n x is equal to f x plus lambda times integral a to x k x comma s y n minus 1 s ds, and this result is valid for n greater than equal to 1. And also we have discussed in detail the convergence of this method. So, that means at every step we are getting a refinement of the function y's. So, first of all we have started with y0x, then we have obtained y1x, then we can calculate y2x, and in general we can calculate ynx. And of course, this sequence of function thus generated, that is ynx, this sequence converges uniformly as we have discussed, and if this sequence converges uniformly and if limit n tends to infinity ynx, this is equal to yx, then this limit function is actually solution of the given Volterra integral equation. Now, in the second case, that is in case of series solution method, in case of series solution method, we have assumed that solution of the integral equation can be obtained into the form, that is yx is equal to summation n runnings from 0 to infinity c n x to the power n. So, that means it can be expressed as a power series of x, and upon substitution this series into the integral equation, we can get summation n runnings from 0 to infinity c n x to the power n. This is the expression after replacing y on the left hand side. On the right hand side, f x remains unaltered, and then we can write lambda integral 0 to x k of x comma s summation n runnings from 0 to infinity c n s to the power n ds, and from here, assuming the convergence of the series, we can interchange the summation and integral sign, and we can write n equal to 0 to infinity c n integral 0 to x k of x comma s s n ds, and from here collecting the coefficient of equal powers of x, we can find out C0, C1, C2 and so on, and of course equating some general term of the form either x to the power n or x to the power n plus 1 or x to the power n plus 2 as for your convenience. From the both sides we can calculate the recurrence relations. After calculating this C0, C1, C2, we can construct the series yx, and if this series converges to a continuous function, then that particular continuous function is a solution to the integral equation. So, in this case sequence of function that is ynx converging to the solution, in this case we are calculating C0, C1, C2 and so on, such that the summation n runnings from 0 to infinity Cn x to the power n, this converges to the solution of the given problem. Now, we are going to consider the method that is called Adomian decomposition method. By this Adomian decomposition method, we are going to solve this integral equation yx is equal to f x plus lambda integral a to x k of x comma s y s d s, again where a less than equal to x comma s less than equal to b, where b is a finite number. For the applicability of this method, we need continuity of f x, that is f x is continuous for all x belongs to a comma b, and k x comma s, this is continuous over the squared domain a b cross a b. If this condition is satisfied, then Adomian decomposition method is applicable. Now, what is this Adomian decomposition method? This Adomian decomposition method is first appeared in the area of solving ordinary differential equation, partial differential equation, integral equation, as well as some nonlinear problems also, where the solution of y x is assumed to be into this summation format, that is n runnings from 0 to infinity y n x. And here we are going to construct one iterative method such that after every step we will be having one terms resulting from the performance of the integration on the right hand side, that one terms of this particular series, such that this summation of the series converges to the solution of the given problem. Now, what is the method? First we will describe the method, and after that I will be coming to the proof of the convergence of this infinite series. Method says that we assume this series converges, that means there exists a solution for this problem, and solution can be expressed as summation over n runnings from 0 to infinity y n x. We are not assuming any particular form of y n x, that is the most important point that you have to understand here. In case of series solution method, we have assumed this will be of the form n runnings from 0 to infinity C n x to the power n. So, that means a power series of x. Now, at this point we are not at all assuming any particular form for y n x, only thing is that each of them will be continuous. Secondly, in case of successive approximation method, using the approximation of the last step, we can get a further modification or better solution for the given problem by approximation step by step. Now, here we are going to find these functions y0, y1, y2, y3 and so on in a systematic manner, such that upon summation of all these quantities we will be having solution to this problem. And of course, in due course of time I will explain what is the advantage of this method and also make a comparative study of this method with the other available methods. So, if we assume this y x equal to sigma n runnings from 0 to infinity y n x is a solution of this problem. So, that means this will satisfy this integral equation. So, if we substitute there, then we can find n runnings from 0 to infinity y n x, this is equal to f x plus lambda times summation n runnings from 0 to infinity integral a to x k of x comma s y n s ds. If we write the terms of this series explicitly, then we can find y 0 x plus y 1 x plus y 2 x plus dot dot, this infinite series is equal to f x plus lambda times integral a to x k of x comma s y 0 s ds plus lambda times integral a to x k x comma s y 1 s ds plus lambda times integral a to x k x comma s y 2 s ds plus dot dot. Now, our target is to construct a iterative method such that with some initial guess for y 0 we can calculate y 1 x. Once we have obtained y 1 x, then we can calculate y 2 x and so on. So, here we are assuming y x equal to f x directly, this y x y 0 x equal to f x. Now, if we equate this as term by term, so first term on the left hand side is equal to first term on the right hand side, then second term on the left hand side is equal to second term on the right hand side. Proceeding in this way, we can get these results, that is y 1 x is equal to lambda times integral a to x k of x comma s y 0 s ds. Then third term on the left hand side is y 2 x is equal to lambda times integral a to x k of x comma s y 1 s ds. Proceeding in this way, the general term y n x, this is equal to lambda times integral a to x k of x comma s y n minus 1 s ds, and here n, this is greater than equal to 1, because this recursive formula is valid for n equal to 1 and onwards. That means, y 1 x, y 2 x, all these iterates can be obtained from the general formula by substituting n equal to 1, 2, 3 and so on. Only there is separate definition for y 0 x. Now, before going to consider any particular example, we will be considering the convergence of this method. So, we have started with the assumption that y 0 x equal to f x. You can calculate y 1 x, because for the given problem kernel x comma s is known. So, substituting y 0 s here, we can calculate y 1 x, then y 2 x can be calculated upon substituting y 1 s here. So, proceeding in this way, you can get every iterates, and hence the solution to the given problem is given by y x is equal to sigma n runnings from 0 to infinity y n x. This will be a closed form of function depending upon the problem, and if we are unable to identify any function in the closed form corresponding to this infinite sum, that is y 0 x plus y 1 x plus y 2 x plus dot dot up to infinity, then we have to leave the solution as it is that appeared from the step by step approximation. Now, we consider the convergence of this problem. You can recall that we have assumed that f x is continuous. We have assumed that f x is continuous over the closed interval a comma b, and k x comma s, this is continuous over the squared domain a b cross a b. Both of these are actually closed sets. So, these continuous functions, they are continuous over the closed sets. So, there exist two positive constants L 1 and L 2 such that f x less than equal to L 1 and modulus of k x comma s less than equal to L 2. This result is valid for all x and s ranging in this particular range from a to b. Now, with this assumption, you can recall f x is continuous. So, if f x is continuous, so first quantity that we are getting for the series of involved with Adomian decomposition method, this is a continuous function, y 0 x is continuous function. Further, this y 0 x satisfies this criteria that modulus of y 0 x is equal to modulus of f x, which is less than equal to L 1. Now, definition for y 1 x, this was lambda times integral a to x k of x comma s multiplied by y 0 s ds. So, taking modulus, we can write modulus of y 1 x, that is equal to modulus of lambda integral a to x k of x comma s y 0 s ds, this modulus. Then taking modulus inside the integral sign, we can write modulus y 2 x, this is less than equal to modulus lambda integral a to x modulus of k x comma s modulus of y 0 s ds, and using the bounds for this y0 x is less than equal to L1 this modulus, and modulus k x comma s, that is modulus of the kernel, is less than equal to L2. So, using these results we can find modulus lambda L1 L2 integral a to x ds, and this is equal to modulus lambda L1 L2 x minus a. Similarly, calculating, sorry, I made one mistake here, this will be y1 x. Then y2 x modulus, as usual it will be less than modulus lambda integral a to x modulus k of x comma s, then modulus y1 s ds, and this is less than equal to modulus lambda. Just be careful about here, modulus k of x comma s is less than equal to L2, and modulus y1 s, this is less than equal to this quantity. So, ultimately we get modulus lambda whole square L1 L2 integral a to x s minus a ds, because here x is greater than a, and within this integral we can recall that a less than equal to s less than equal to x. So, we can withdraw modulus sign from x minus a when it is coming under this integral sign. So, after performing the integration, it is coming out to be L1 modulus lambda whole square L2 square x minus a whole square divided by 2. Similarly, for modulus y3 x, we can calculate this is less than equal to modulus lambda, then integral a to x modulus k of x comma s modulus y to s ds, and after performing this integration and substituting this limit, we can find this will be less than equal to L1 times modulus lambda whole cube L2 cube x minus a whole cube whole divided by factorial 3. This will be the bound for modulus y3 x. So, in general we will be able to prove that modulus y n x, this is less than equal to L1 times modulus lambda whole to the power n L2 to the power n x minus a whole to the power n divided by factorial n. This is the modulus for y n x, and now we can recall that result we have assumed a less than equal to x less than equal to b. So, with this range for x, we can write modulus y 0 x as usual less than equal to L1 that we have obtained at the very first step from the assumption on f x. Then from general term modulus y n x, this is less than equal to L1 times modulus lambda whole to the power n L2 to the power n x minus a to the power n by factorial n. This is less than equal to L1 times modulus lambda whole to the power n L2 to the power n. Now, this x is always less than equal to b. So, therefore, b minus a whole to the power n divided by factorial n. This result is for n equal to 1, 2, 3 and so on. So, for this entire range it is valid, and therefore, summation n runnings from 0 to infinity modulus of y n x, we can write this is less than equal to L1 plus summation n runnings from 1 to infinity L1 modulus lambda whole to the power n L2 to the power n x minus a whole to the power n by factorial n, and taking L1 common we can write this is equal to L1 times e to the power modulus lambda L2 b minus a. So, that means the summation of the modulus of the terms of y j x, these are uniformly bounded and this bound is free from x term. So, that means the series summation n runnings from 0 to infinity y n x converges uniformly. So, this is actually the proof of the uniform convergence of the series sigma n runnings from 0 to infinity y n x. So, based upon the continuity of the function f x and continuity of the kernel x k x comma s, we can prove that this series of Adomian polynomials, these y n x sometimes called as Adomian polynomials, the summation of these Adomian polynomials converges to the function y x uniformly, which is a continuous function, because from the every step you can easily verify that once y 0 x equal to f x is continuous, then if y 1 x will be continuous upon evaluating the integral. Similarly, substituting y 1 x into the formula, you can get y 2 x is continuous. So, every y n x is continuous and also they are uniformly bounded. So, this proves the uniform convergence of the series to a continuous function, and if we call this particular continuous function as capital Y x, then y x is equal to capital Y x is the solution of the targeted problem. Now, we consider one example to understand this method. So, we considered this example already we have considered earlier also using different methods to solve it, but again I am considering this problem in order to make a comparative study. So, this is x minus s y s d s. So, as per the method that we just discussed, y 0 x equal to f x equal to x, because x is the non homogeneous part, and then applying the formula we can find y 1 x, this is equal to minus integral 0 to x x minus s s d s, and after integration it will be x into x square by 2 plus x cube by 3. So, that is equal to minus x cube divided by 2 into 3, and calculating the third term, that is y 2 x, this will be minus integral 0 to x x minus s, then y 1 s is minus s cube by this. So, minus s cube divided by 2 into 3 ds, and this will results in, after some calculation, that x to the power 5 by factorial 5, and just one more iterates you can calculate, it will be minus integral 0 to x x minus s s to the power 5 by factorial 5 ds, it will results in minus x to the power 7 by factorial 7. So, y x is going to be this summation n runnings from 0 to infinity y n x. So, this is sum of the term x minus x cube by factorial 3 plus x to the power 5 by factorial 5 minus x to the power 7 by factorial 7 plus dot dot up to infinity, and you can easily recall this is the series that is sin x. So, sin x is a solution of this equation that we just obtained using the Adomian decomposition method. Now, just for a comparative study, you can recall that when we are going to solve this problem, or we have solved this problem by successive approximation method, for successive approximation method of the same problem, we have obtained y0 x is equal to x, y1 x this is equal to x minus x cube by factorial 3, y2 x this was x minus x cube by factorial 3 plus x to the power 5 by factorial 5, and so on. So, in this case we have to integrate this entire function evaluated in terms of or written in terms of s, and substituting into the integrand, pre-multiplying it by x minus s, and ranging from 0 to x, we have obtained the third approximation. But in case of Adomian decomposition method, the labor of integration is comparatively less, as we have adopted in the case of successive approximation method. So, instead of getting some extra terms at each iterates, these y0, y1, y2 up to yn, then sequence ynx converges to the solution, but in case of Adomian decomposition method, we are getting each terms, that is x minus x cube by factorial 3 plus x to the power 5 by factorial 5 at every steps of the iteration. And once we solve the same problem with the help of series method, series solution method, then little bit of difficulty was to construct the general nth term, to construct the recursive formula. And for that recursive formula, you can recall we have used this result yx is assumed to be summation n runnings from 0 to infinity c n x to the power n, and after substitution we have obtained c0 plus c1 x plus c2 x square plus dot dot, this was equal to x minus c0 x square by 2 minus c1 x cube by 2 into 3 minus c2 x to the power 4 by 3 into 4 minus dot dot, and with some initial conditions we have obtained c0 equal to c2 equal to c4, all these quantities are exactly equal to 0, and then these results are obtained with help of this recursive relation, that is c n plus 2 equal to minus c n by n plus 1 multiplied with n plus 2, but this recursive relation was not valid for some initial steps, that is from where we have calculated c0 equal to 0 and c1 equal to 1, and with these iterates we have calculated that c1 this is equal to 1, c3 is equal to minus 1 by factorial 3, and c5 is equal to 1 by factorial 5, and so on, and then substituting into the series we have obtained the same solution. So, this is actually prominent difference between the two methods. Now, there are some limitations of this method. It is not true that every problem it would be better to use Adomian decomposition method to obtain the solution. In order to understand the problem that may arise to apply this Adomian decomposition method, here we consider one more example. Suppose we have to solve this problem yx, this is equal to 1 plus x e to the power x minus integral 0 to x s y s ds. This is the given problem. So, clearly the non-homogeneous part f x is equal to 1 plus x e to the power x. As per described method, here y0 x is equal to 1 plus x e to the power x, and then if we going to calculate y1 x minus integral of 0 to x s into 1 plus s e to the power s ds, this one, and you can clearly understand one part can be evaluated very easily, that is the first part x square by 2, but for the second part we need the repeated application of the bypass integration, that is a square e to the power s ds, and if we evaluate this integral completely, then we can find this will be x square by 2 minus with bypass integration it will be a square e to the power s, because first step we have to keep a square unaltered, that is this is u, this is v. So, by integrating e to the power s, a square e to the power s minus 2, it will be integral of s e to the power s, and after integration it will be s e to the power s, and then plus 2 e to the power s, this limit 0 to x, and after substituting the limit we can find this will be 2 minus x square by 2 minus x square e to the power x plus 2 x e to the power x minus 2 e to the power x. Now, from this expression, now you can clearly understand it will be very difficult to calculate y to x with this as the integrand. So, we have to be very much careful for the choice of the particular method with which we are going to solve this equation. So, in this case the standard Adomian decomposition method is not giving us very easy way to obtain the solution of this problem. Now, this Adomian decomposition method is modified further, that is called modified Adomian decomposition method, and this particular method is applicable for the problems like suppose we have to solve this problem y x is equal to sec square x plus 1 minus e to the power 10 x multiplied with x plus integral 0 to x e to the power 10 s y s ds, where x is less than pi by 2. Now, in this problem if we choose this entire quantity, that is sec square x plus 1 minus e to the power 10 x into x as f x, then again it would be very difficult to apply the Adomian decomposition method. So, in this case we have to use the modified Adomian decomposition method. This modified Adomian decomposition method says the target equation is y x equal to f x plus lambda integral a to x k of x comma s y s ds, a less than equal to x comma s less than equal to b. We are intended to get solution into this form, n runnings from 0 to infinity y n x. Modification is that we have to divide f x into two parts, f 1 x plus f 2 x. This decomposition means that sometimes we have to take f 1 x consist of 1 or 2 terms, such that the integration in the successive steps will be very much easier. And just for a quick reference, you can have a look at this expression. This integral equation under this integral sign contains x e to the power 10 s times y s ds. So, variable of integration is s. So, we can take x outside. So, in this case if we having this y s as sec square s, which is already present here in terms of x. So, then it will be very easy to integrate this evaluate this integral. So, for this kind of problem here f x can be divided into two parts, such that other iterates can be obtained very easily. So, we have to decompose f x into two parts as f 1 x plus f 2 x, and then we have to substitute into the expression that we have described earlier, and if we substitute there. So, we will be having terms like y 0 x plus y 1 x plus y 2 x plus dot dot, this is equal to f 1 x plus f 2 x plus lambda times integral a to x k x comma s y 0 s ds plus lambda times integral a to x k x comma s y 1 s ds plus dot dot, and here we have to equate y 0 with f 1 x, then y 1 x is equal to f 2 x plus the first integral appeared on the right hand side, and then y 2 x equal to, as we have adopted earlier, that is lambda times integral a to x k x comma s y 1 s ds and so on. So, that means, in the modified Adomian decomposition method, the iterates will be y 0 x is equal to f 1 x, y 1 x this will be equal to f 2 x plus lambda times integral a to x k of x comma s y 0 s ds, and then y 2 x is equal to lambda times integral a to x k x comma s y 1 s, and then other higher iterates will be similar. So, that means, it will be a to x k x comma s y 2 s ds in this way. So, that means, general iterates will be y n x is equal to lambda integral a to x k x comma s y n minus 1 s ds. Now, here this iterated formula is valid for n greater than equal to 2. So, that means, if we combine these results for modified Adomian decomposition method, so first iterate y 0 x is equal to f 1 x, y 1 x is equal to f 2 x plus lambda times integral a to x k of x comma s y 0 s ds, and then general iterate y n x, that is equal to lambda times integral a to x k of x comma s y n minus 1 s ds, where n greater than equal to 2. So, this is the actually compact form of the Adomian decomposition method, that is of modified type. Now, with this method we solve this problem with which we have started this discussion on modified decomposition method. So, given problem was y x is equal to sec square x plus 1 minus e to the power 10 x multiplied with x plus integral 0 to x x e to the power 10 s y s ds. So, we are assuming that f 1 x this is equal to sec square x and f 2 x this is equal to 1 minus e to the power 10 x this multiplied with x. So, with this f 1 and f 2, so our first component y 0 x is equal to sec square x, and interestingly if we calculate y 1 x. So, this will be 1 minus e to the power 10 x this multiplied with x plus integral 0 to x x e to the power 10 s multiplied with sec square s ds. Now, here the variable of integration is s. So, we can take this x outside the integral sign, and then assuming this tan s equal to u, this integral will be reduced to integral e to the power u du. So, then after evaluating the integral, we can find 1 minus e to the power 10 x multiplied with x plus x e to the power 10 s, this limit will be from 0 to x. So, after evaluating you can find this tan x multiplied by x plus x e to the power 10 x minus 1. So, this is exactly equal to 0. So, once this y 1 x is exactly equal to 0, so immediately you can understand that y2x, y3x and so on, all these components are exactly equal to 0, and therefore, yx, that is assumed to be n runnings from 0 to infinity ynx, this is nothing but simply y0x is equal to sec square x. This is actually solution of the given problem. So, that means, if we going to apply any other method, it would be very difficult to find solution of this particular integral equation. You can verify with yourself by the method of successive approximation. That will be little bit problematic, because with this entire expression, if we assume this as y0x, then it will be little bit difficult to calculate y1x and so on. Series solution, you can clearly understand that is difficult, because this integrand involve e to the power tan s. So, there is no possibility to obtain this integral in a closed form, apart from this applying some iterative formula or some reduction formula. So, best possible way to solve this integral equation is the modified Adomian decomposition method. So, you have to keep in mind that based upon the given problem, you have to choose the method appropriately. Before coming to the end of today's lecture, we can look at the convergence of this method. In this case, we have assumed that f x can be expressed as summation of two functions f1x and f2x. So, again these two functions are actually continuous functions, k x comma s, this is continuous over the square a b cross a b. So, we are assuming that modulus of f1x, this is less than equal to L11, modulus of f2x, this is less than equal to L12, and modulus of k x comma s, this is less than equal to L2. So, what will going to happen in the successive steps? First step, modulus of y0x, that is less than equal to, sorry, it will be exactly equal to modulus of f1x, and this is less than equal to L11, then modulus of y1x, this is equal to modulus of f2x plus integral a to x with lambda k x comma s y0 s ds, this is less than equal to modulus of f2x plus modulus of lambda integral a to x modulus of k x comma s modulus of y0 s this ds, and this will be less than equal to L12 plus modulus of lambda L11 L2 times x minus a. Just have a look at this expression. Here modulus k of x minus s, this is less than equal to L2, this modulus of y0 s, this will be less than equal to L11. So, ultimately it will result in modulus lambda L11 into L2 multiplied by x minus a. Similarly, modulus of y2x, this is equal to modulus of lambda integral a to x k of x comma s multiplied by y1 s ds, which is less than equal to modulus lambda integral a to x modulus of k x comma s modulus of y1 s ds, this is less than equal to modulus lambda L2 integral a to x modulus of L12 plus modulus lambda L11 L2 times S minus A, this modulus ds, and after applying this modulus, that is mod of this is less than equal to modulus of L11 plus this quantity, and L11 is positive. So, ultimately you will be having that modulus of L lambda into L2 times L12 multiplied by x minus a plus modulus lambda L11 L2 x minus a whole square divided by 2. So, we are having one particular terms of the form, that is L11 L2 modulus lambda x minus a, this is coming from here, and here we will be having this modulus lambda L12, it will be L2 square modulus x minus a whole square by 2. So, in this way if you calculate modulus of y3x, it will be less than equal to modulus lambda whole square L12 multiplied with L2 square, then x minus a this whole square divided by 2 plus modulus lambda whole cube L11 L2 cube x minus a whole cube divided by factorial 3, this will be L11. So, in this way you will be having modulus of y n x is summation of these two, and afterwards you will be able to prove that summation n runnings from 0 to infinity modulus of y 1 x, this will be actually less than equal to L11 plus L12 e to the power L2 modulus lambda times b minus a. This is the result, and therefore, this sequence some of the series is uniformly convergent, and this solution is given by y x is equal to sigma n runnings from 0 to infinity y n x. So, this is the final solution of the given problem. So, we have started with the Adomian decomposition method, where we have assumed the solution into this form y x equal to summation n runnings from 0 to n y n x, and with the definition of the first iterate y 0 x equal to f x, and then y n x equal to lambda integral a to x k x comma s y n minus 1 s ds n greater than equal to 1, we have obtained this is method is called the Adomian decomposition method. And then we have considered one example where we have seen that it is difficult to carry out the calculations for y 0, y 1 and etcetera if we use the standard Adomian decomposition method. So, we can adopt the modified Adomian decomposition method to solve this kind of problems. And before coming to the end, just for a quick example, you can consider this one, that y x is equal to x cube minus x to the power 5 plus 5 integral 0 to x s y s ds. If you just have a clever look at this problem, so if we are able to substitute here y s equal to s cube, so after integration it will produce an x to the power 5. So, in this case again the modified Adomian decomposition method is very useful. So, f 1 equal to x cube, if you use this is equal to y 0 s. So, y 1 s will be equal to minus x to the power 5 plus 5 integral 0 to x s into s cube ds, this is equal to 0, because this will result in x to the power 5 by 5. So, minus x to the power 5 plus x to the power 5 equal to 0. So, y 2 s and other expressions y 3 s, all of them will be identically equal to 0. So, easily you can find y x equal to x cube. This is a solution for this problem. So, today I can stop at this point.